Hello and welcome to Week 10, Lecture 2 of CO 442642 Graph Theory. Today we'll be discussing the Erdos-Stone Theorem. So what we'll be talking about today is the Erdos-Stone Theorem, which revolves around Turan numbers, which we learned last week. To remind you what is a Turan number, the Turan number of a graph H, denoted Ex and H, is the maximum number of edges in a graph on n vertices that does not contain H as a subgraph. So it's the maximum we can get in an H-free graph. And the theorem by Turan from 1941 gave the Turan number of the complete graphs. It said that Ex and of Kr was this Tr minus 1 of n, that's the number of edges in the Turan graph, which is at most 1 minus 1 over r minus 1 of n choose 2 as an upper bound. But there's the, as we went through when we discussed Turan's theorem, there's a more specific function that's close to that, but is attained by the Turan graph. But a question that we asked then, that we left off answering, is for every graph H, what is the Turan number of H? What is Ex of n comma H? And that's what we'll answer in part today. To do that, we will need the Erdos-Stone Theorem. To state it, let us denote by K S star R the complete R-partite graph with S vertices in every part. Equivalently, this is kind of the Turan graph with R parts on RS vertices, where you have the equitable parts. So you can also think of it kind of as a blow-up of the complete graph, into where every vertex gets blown up into an independent set on S vertices. Given that, we can now state the Erdos-Stone Theorem by Erdos and Stone from 1946. It says that for every integers r at least 2 and s at least 1 and every gamma greater than 0, there's an integer n0 such that every graph with n at least n0 vertices and at least tr minus 1 of n plus gamma n squared edges contains this ksr as a subgraph. So let's unpack that a second. It's saying that if you are large enough, so the number of vertices is large enough, bigger than this n0, which is determined by the other parameters, then it says that as long as we have kind of slightly more than the number of edges in the Turan graph, where slightly more is this gamma n squared. So kind of quadratically, we have just a little bit more, then we can not only get, of course, a kr subgraph, but actually any blow up of it. So any complete R-partite graph with S vertices in every part. So if you fix your R, you fix your S, and you fix gamma, then as long as n is large enough with respect to those. So basically, asymptotically, this tells you kind of the Turan number of these blowups is asymptotically the same as just for Kr. And actually, it tells you more than that, if you think about. So back to Turan numbers. As a corollary, we basically determine the Turan number of almost every graph. So this was realized by Erdos and Simonovich in 1966. And so they proved that for every graph H with at least one edge, the Turan number of H is 1 minus 1 over chi of H minus 1 plus little o of 1 and choose 2. So this is quite a beautiful theorem. It's saying that basically for every graph, the Turan number is determined by its chromatic number. So chromatic number actually plays an important role in Turan numbers, even though you would think they don't have any relation. But if you only knew about Turan numbers, you would kind of discover the idea of the chromatic number from them. So that's one takeaway from the Erdos-Simonovich theorem here. But this is actually just a corollary of the Erdos-Stone theorem. So let's go ahead and prove that. So how would you do it? We'll let R be this chromatic number of H. And now maybe you see the connection. So why do we know it is a lower bound? Well, then H is not a subgraph of the Turan graph Tr minus 1 of n, right? Because that would be, the Turan graph is clearly R minus 1 colorable, it's R minus 1 partite, so we couldn't embed H, we couldn't find H as a subgraph there. So this would immediately tell you that the Turan number of H is at least kind of Tr minus 1 of n, so the Turan number of Kr. But it would also, on the other hand, we know that H is a subgraph of a complete R-partite graph with S vertices in every part, where, for example, S you could take to be the number of vertices of H. So then certainly H would be a subgraph of that, right? Because it has chromatic number exactly R, it has an R partition, and therefore we could embed it. And then we would know that, of course, as a subgraph, then the Turan number of h is the most of the Turan number of that blowup, which would then be tr minus 1 of n plus little o n squared vertices. So asymptotically the same, which becomes the little o of 1 in the formula. So really this KRS, these complete multipartite graphs, capture the essence of the chromatic number. And so by proving the Erdos-Stone theorem, you're really actually, even if it doesn't sound like it's about Turan numbers, it's really about Turan numbers of the complete multipartites, but then that's really gives you the Turan numbers of basically all the graphs. Except I should mention, you should notice what happens though if h is actually bipartite. So if chi of h is 2, then that 1 over chi of h minus 1 becomes a 1, the 1's cancel, and you just get little o of 1. So for bipartite graphs, it's known that they're little o of n squared. So basically every dense enough graph contains any bipartite graph. So that's nice, but it doesn't actually tell you what exactly the number. It just tells you it's little o of n squared. So there's much research and it's still open what are the actual exact the Turan numbers of bipartite graphs. But we won't get into that. But basically for every h that has chromatic number bigger than 2, then this really determines the Turan number for those. It's basically asymptotically the same as it is for KR. Okay, so that's the Turan numbers. We're going to move on toward proving the Erdos-Stone theorem. But our proof of the Erdos-Stone theorem will not be the original proof. Instead, we've set it up that we're going to use an easy application of a version of a corollary of the regularity lemma. So we're going to use the regularity lemma, and this corollary is called the blow-up lemma. So we went all this trouble to define the regularity lemma, which is nice in its own, and to prove it. And though the proof is interesting, the applications are actually somewhat more interesting. And one of those applications will be this blow-up lemma, which we'll get to and we'll define and state in a second. But from that, we'll be able to rather easily derive the Erdos-Stone theorem. All right, so how do we state? Well, first we need to define a regularity graph. So this is quite natural. If you have a graph G and an epsilon regular partition V0, V1 up to Vk, where V0 is of course the exceptional set, and say all the V1s, Vk, they're equitable, so say they're all equal to L, then I can define the regularity graph R of G with parameters epsilon L and D in 0, 1. What will that be? The graph, well, we'll forget about the exceptional set, so throw out the trash, and we'll have the vertices be the sets. So just contract, kind of make every part just its own vertex. So we think of each part of the regularity partition as a vertex, V1 up to Vk, and we put an edge between the two parts under two things. We need that Vi, Vj is an epsilon regular pair, so it's not allowed to be one of those few irregular pairs, and we require the density to be at least D, so to be somewhat dense. In this case, we put an edge. So maybe now you see that where the epsilon plays a role, because it's the epsilon regular partition, and we're throwing out the irregular pairs. L is just to give us a sense then of the size, and then D will tell us that there's density. There's density, at least D on all those pairs. So it makes a lot of sense. It's kind of, if you use D as a threshold by which to recognize kind of a pair, an edge in this regularity graph, then if we squint in, we can't see the trash, we can't see the irregular pairs, and we can only see kind of dense enough, but if we stare at it, then those kind of edges will pop out to us, and the other ones will kind of fade into being non-edges. And in this way, we have a regularity graph. So it's a useful concept, and from that, we'll be able to state the blow-up lemma. To do that, let's take a regularity graph. We let R sub S denote the S blow-up of R, which we've kind of mentioned before, but let's again go over that. It's where you take every vertex, so here this is a Vi, we'll blow it up and replace it by a set of Vi, we'll use S in the superscript there to denote this set of S vertices. So you blow up each vertex into S independent vertices, and every edge is replaced by a complete bipartite graph on those, so KSS on those vertices. So that's the S blow up of R, so kind of we shrunk down to the regularity parts, only kept the dense regular pairs. We could blow it back up into sets of size S. And then the blow-up says the following, that for every D in 0, 1, delta at least 1, that there is some epsilon 0, such that if you give me a graph G and a regularity graph for G, so let's call that R, with parameters epsilon, L, and D, and importantly, H, a new graph here, is a subgraph of my blown up regularity graph of RS with maximum degree at most delta, then actually we can find H as a subgraph of G. Provided, so this is where the epsilon 0 and things come in, that epsilon is small, so it's at most epsilon 0, and L is at least 2s over d to the delta, so that the parts are large enough. So we're going to prove this, but let's maybe, again, I'll just process that in words. So the blow-up lemma is saying, I give you a graph, I give you this regularity graph. Well, maybe you see the regularity graph has a clique. Does that mean like the original graph does? But yes is kind of saying what it's saying, provided some assumptions, but it's even more than that. It's kind of saying, well, actually, even if I blew up my regularity graph, took a blow up, if I could embed a graph H into that blow up, then I should be able to find it in the original graph. So of course, this will be useful for the Erdos-Stone Theorem, where we're not looking just for cliques, but for blown up cliques. So H would be a candidate there. But it'll be even useful when we get back to Ramsey numbers, because it's saying that as long as actually you have maximum degree delta, then you can do it in a way that's kind of linear in the blow-up S, but though it might be exponential with the delta. So if you care about the parameters, then we make that distinction. The main takeaway, though, being, if we can find a graph in the regularity graph, then we can kind of not only find that in the original graph, but also blow-ups of it. And again, provided that your epsilon, that it's small enough. So we're just saying there's some epsilon 0 where every small enough one, every epsilon that's smaller. And of course, we require the parts to be large, which makes sense because we need lots of vertices to try to find this blow-up. So that obviously has to be kind of at least S, but you're going to have to actually account for D being not very dense. Okay, so now that you've processed that statement, we'll work on proving the blow-up lemma, and then we'll return to derive the Erdos-Stone Theorem from it and close out the lecture. But blow-up lemma will take some work. So we're going to need a lemma first about epsilon regular pairs. So to do that, let me define some notation. Let G be a graph and Y be a subset of the vertices. We let NKY, and this really isn't standard at all, but just be useful for a proof of the blow-up lemma, be the set of vertices with at least K neighbors in Y. So if giving me that notation, then here's a nice lemma. If let AB be an epsilon regular pair of density D, so of course I mean, in some regularity graph R for some graph G, but let me ignore that. Then if Y is a subset of B, with Y being large, so at least epsilon times B, then we claim that if you take A and remove n d minus epsilon YY, that's the neighbors with at least d minus epsilon Y neighbors in Y, then that set is at most epsilon A. So in words, this is saying that, there are fewer than epsilon A vertices that have strictly fewer than d minus epsilon Y neighbors in Y. So basically, if you take any large subset of B, if randomly, since you have density D, you'd expect around dy neighbors, but things aren't perfect, so maybe d minus epsilon Y is within kind of the tolerance for epsilon regularity, but really anything smaller than that, anything with fewer neighbors is unlikely. So there'd only be a few vertices, most epsilon A, that really have too few neighbors in this Y. And we kind of suggested that with the idea of epsilon regular and kind of being random-like in that the neighborhoods are kind of spread. This is really quantifying that, and we can actually just derive it directly from kind of the definition of epsilon regular. So how do we do that? We'll let X be the set, right? So take the set with not too many neighbors, and the key is then think about how many edges go from X to Y. Well, every vertex in X has at most, strictly fewer than d minus epsilon Y neighbors. That was the definition there. So that means the number of edges between X and Y, this double bracket XY, is less than X times d minus epsilon Y. Now, if you divide through by X and Y, the sizes there, that becomes d of XY, the density. So that would tell you the density of xy is strictly smaller than d minus epsilon, and d by definition was d of ab. So d of xy would be smaller than d of ab minus epsilon. Now that should provoke bells for you because, right, this difference between dxy and dab was something crucial to the definition of epsilon regular pair. Namely, we knew that by definition of what it meant to be epsilon regular, that, if AB is epsilon regular, that if you had two large subsets, an x and a y, then actually their density had to be within an epsilon of d. Since y is large, it's at least epsilon b, that means that x is not large. Where large here means then that x must be smaller than epsilon times a, which proves our lemma. So you can think about that, but really, that's what epsilon regularity gives you. All right, so now we can prove the blow-up lemma. So to prove the blow-up lemma, it's of course key, you have to choose this epsilon naught. That was our one toggle we had. We have to choose it small enough. So it turns out small enough here will be, if you take it small enough so that d minus epsilon naught to the delta minus delta epsilon naught is at least a half d to the delta. So you kind of choose it in a way that if you kind of take that power to the delta and also even subtract off delta epsilon, then you don't lose too much, only a factor of 2 there. So you can do that. So let's just assume we've done that. Then that can be our epsilon naught. And then our key is going to be, so how should you think about this? Now we have this graph H that lives in your RS. So let's label it V1 up to VH. So V of VH, let's just give it a labeling. And let Ri denote the actual set that Vi belongs to in the regularity partition. So Vi would be in this Vs sub Ri. So kind of the index, what is its regularity part. Now given me that, I can now prove one claim that basically just proves the whole lemma. And then we'll use some slides to prove this claim. So here's our strategy. Our strategy is we're going to embed H, one vertex at a time. So what does that mean? We're going to do it in stages. So for all I, 0 to V of H, so there'll be kind of V of H stages. They'll exist distinct U1 to Ui and V of G. So, we're going to, we have the V1s, V up the vertices of H, we're going to kind of embed them. So we're going to find images. These are going to be the U's, U1 up to Ui in V of G. And we're also going to have to worry about how to embed the rest of the graph. So we're going to define sets called Tij's. These will be subset of the VRJs, so they'll be targets. So you kind of want to know, so somehow, I want to go from where they were in the blowups to where they are in the graphs. So from the VRJ with S as a superscript to just VRJ. So I know I want to be in this part, so we'll have target sets for the vertices. So Uj, whenever we get around to embedding it, we'll put it into the target Tij. And we'll do that subject to some conditions. So we're kind of going to iteratively do this. So we're going to kind of start with everything being possible targets for the vertices of H, for at least starting with their parts, and then we're going to refine. So we'll do this with a number of conditions. So one, we'll make sure that we've embedded the graph. So that means that if you take H induced on V1 up to Vi, it's a subgraph of G induced on U1 up to Ui. So we really embed it, and I mean in the label sense there. So we really have embedded the graph. Maybe we have extra edges, but we at least get H. Two, we're going to make sure that, we have to still embed the rest of the vertices. So you want to ensure that the target sets are subsets of the neighbors of previously embedded, right? So if you had, if you had a VK that's a neighbor of VJ where K is in some I, we want to make sure that our target sets are subsets of the ends of the UK. So we want to make sure that, our target sets are constrained by, they have to be neighbors of things that are already embedded if they're going to be acceptable kind of candidates or targets for later vertices. That's condition 2. And number 3, we just want to make sure we have target sets left. So we want to control how the target sets are, namely that they're large. So the claim is that the target set Tij will be a d minus epsilon kind of to some power proportion of Vrj, where that power is the number of neighbors of Vj in the earlier vertices, V1 to Vi. So for each earlier neighbor, you're going to lose a factor of d minus epsilon, which should remind you from kind of that previous lemma and the expression for the choice of epsilon 0 above. So these are our three things. I like to embed the vertices of H, so that's condition 1, that we're embedding them. Condition 2, we have these targets, and that the targets are subsets of the neighbors of earlier vertices. And condition 3, that the target sets are large. Okay, given that, well, the lemma just follows from this claim, because when you reach the last stage, when I is v of h, you've just embedded the whole graph. And then you don't worry about targets, there's just the vertices, there's the graph, and we're done. We found h. That was the goal. So now you can kind of see it's algorithmic, so we'll just prove the claim. We'll do it by induction on I. When I is 0, what do? You just set the target sets to be the whole part that they could potentially live in. And then there's really no condition. I mean, those parts have the correct size for condition 3. There's nothing yet embedded, so we don't worry about the neighbor condition. So all that works. Then we assume I is greater than 0. And what's the trick is we're going to pick a UI in the target set. So that would be ti I minus 1, so from the previous target set. And then what we do is we know that, so that should be si, not sj, sorry for the typo there. Then what we do is we intersect all of the future neighbors. We make sure that we have a lot of neighbors in there, right? So we're going to have to shrink those target sets by whether, I'm a neighbor to those vertices. We're going to have to ensure that the vertex we choose, that they're in their neighborhood. So you kind of want to ensure there's lots of choice for them. And to do that, you just make sure you only pick a target which has at least d minus epsilon tij neighbors in every future tij for any neighbor j, a vj of vi. And this will only work because if you just do out the math, this set will what? It could lose a d minus epsilon for each previous neighbor from condition 3. And when we now do this, so you could upper bound that by or lower bound that by a d minus epsilon to the delta, and we could throw out potentially, if it's the first of its neighbors, a set, we could throw out delta sets of size epsilon. So this is where we're using the lemma from before, because how many vertices don't have that many neighbors is kind of epsilon times the vrj, the epsilon of the set. So if we throw out that for each later neighbor, we'll throw out a most delta epsilon of them. And then the way we chose epsilon naught was that this number is going to be at least half of d to the delta times L, which will be bigger than S, right? So the way we did it is that number is at least half of d to the delta. Vrj is just the size, so that's L, and the condition on L required then that number be at least S, which is great. Why do we want it to be at least S? Well, I played a little fast and loose here on the target sets. Of course, we want the vertices to be distinct, right? So we didn't throw out from the target sets whether previously chosen UIs, so you have to account for that. So here we have to account and say, okay, well actually, I want to be distinct from all the previous UIs in this set, so we ignore them, we just greedily avoid them. We can do that if your size at least S. Why? Because the assumption, remember, that you are a subset of RS, the S blow up. So you only ever have to choose S vertices in a part. So as long as it's always at least S, then there's a most S minus 1 previously chosen ones. If we have to choose one more, we can avoid it, and then we're good there. And we played a little fast and loose because really you'd have this with epsilon instead of epsilon naught, but epsilon smaller than epsilon naught, so you can check that function's actually kind of decreasing in epsilon. So therefore, yeah, this would be at least with the epsilons, but that's at least the epsilon zeros, and then you're good. So, of course you could read D-Stool to get, go through these in more detail, or you can pause and think about that, but that's really the key there. So again, sorry about the typo, Sj should be SIs there, and Vrj should then be Vri, but that's what you end up with. So that means that 1 holds, right? So we proved that we actually embedded the graph And of course, because we chose it from the target set, means that you already have all the neighbors you want. But more than that, the way we chose it, we're now prepared to get the other conditions. So namely, for the target sets Tij, there's really no other choice but then to set Ti minus 1j as the, take that and just make sure you're neighbor to Ui if their edge is present. And if it's not, then you don't have to do anything, so you just keep the target set as is. So that should be a Ti minus 1, again, j there. And then hence 2 holds. And now you just have to check the sizes. So since we made sure that Ui had many neighbors in the Tij, then we're basically done. We're going to get that your Tij there has at least Ti minus 1, you have a d minus epsilon factor for all such j. And then if you're not a neighbor, then you don't have to do anything. You're not changing the size, so that's okay. And so either way, it turns out that condition 3 holds as desired. So that proves the claim, which proves the blow-up lemma. And then we're done. So that's the blow-up lemma. Now let's move on to the Erdos-Stone Theorem. To do the Erdos-Stone Theorem, it's really just an application, right? So you're just going to apply the blow-up lemma. We have to choose what d and delta are. So delta will just take the maximum degree of our KSR blow-up. D will be equal to gamma. So it turns out you want to pick kind of d small enough as it is in the right way. So then here we choose d to be kind of our gamma. So there's some art to picking the right d there, but it turns out that that's the one that will work. And then the other thing we have to do is we have to choose epsilons and L's. So we want to make a regularity graph. So I won't get into the details again, you can read D still, but the key is basically you just choose epsilon small enough. As long as you choose it really small, satisfying some inequalities, that will be fine. And then you need to also choose L to be kind of large enough. Namely, we need it that L is at least 2s over d to the delta. So again, that L, the size, will depend on n and the number of parts. The number of parts would come from, your epsilon, what epsilon you chose, and what minimum number of parts. So you'd have to think about those, but basically we could end up choosing, since n is going to go off to infinity, we're doing this really asymptotically, n just needs to be something large enough to guarantee that condition on L for the blow-up lemma. And then you just consider the regularity graph of G which exists, of course, by the regularity lemma, with k parts and parameters epsilon, L, and d. And then we're almost done. The case 1 is that R contains kr. So if R contains kr, then we're basically done, because by the blow-up lemma, we would get this H. We'd get, KSR would be a subgraph of the RS, the blow-up, the S blow-up of R, with max degree, of course, the most max degree of itself. So that part will work, and we'll have our nice graph, and that's where we needed the conditions on L, and also epsilon has to be at most epsilon naught from that thing. So that's where some of that comes in. And then case 2 is that R does not contain KR. So kind of the point is either your regularity graph contains a clique, right, and then you can find a blow-up of that clique by the blow-up lemma, or if it doesn't, you can invoke Turan's theorem on the regularity graph. So this is the really nice part, where we know that the number of edges in R by Turan's theorem, since it doesn't have a KR, has to be at most TR minus 1 of K, where K is the number of parts there, not counting the exceptional set. And that's at most 1 minus 1 over R minus 1 of K choose 2. And then at that point, you can just argue that E of G is too small, a contradiction, because what's the assumption? The Erdos-Stone Theorem assumes that you're at least kind of TR minus 1 of N plus some gamma N squared. But here, E of G would be at most, well, you have the edges in the regularity graph. Those ones have density at least D, but really they could just have density 1. So they'd have E of R times L squared. And then you have these other terms, but the claim is if you have these other terms, then it's still going to be, and that should be strictly smaller than the number of edges we're supposed to have, and that's a contradiction. So what are these other terms? Well, you have to account for a lot. You have to add in the trash, right? So the trash is size at most epsilon n, so there's at most epsilon n squared edges incident with the trash. That's that second term. You have irregular pairs, of which there's epsilon k squared of them. And again, those irregular pairs could be completely kind of dense, say, dense-ish, but just irregular. So let's just upper bound that with, they could have epsilon k squared L squared. And then you have low density pairs. And how many low density pairs do we have? Well, you know, it could be really just the whole thing could be low density, really. So there are most k choose 2 of those, and each of them, you know, could have L squared, but again, low density, so really you have at most d times L squared. So now if you think about what this says, you go through it, well, ER times L squared is basically at most TR minus 1n roughly. We have an epsilon n squared for the trash. The epsilon k squared L squared, well, k times L is at most n, so that's at most epsilon n squared. And then d is small, right? So we get k squared L squared over 2, that's n squared over 2, and d is at most gamma. So kind of the d accounts for half of the gamma there, and we have like 2 epsilon n squared. So if epsilon is small enough, then that's also smaller than gamma, and the inequality follows. So again, you can think through that, but basically, you know, the trash, if we choose epsilon small enough, the trash is small enough, the number of irregular pairs is small enough, and if we set the density low enough, that's also low, and then we just get a contradiction. Okay, so that's the main idea. The devil's in the details of choosing the parameters all right, and that's very natural to extremal, that you're going to have a lot of parameters and you have to choose them correctly. But basically, you know, once you've set them in the right order and then you choose things small enough and large enough to satisfy certain inequalities, it will work out. But so the main takeaway on a high level is the use of the regularity graph to say, oh, this is really just Turan's problem, right? Either it's there and we can blow it up, or it's not, and then Turan's theorem tells us that's really kind of the number of edges, except for kind of the low stuff, low density, the irregular, the trash, which is a small number of edges. And I'll just point out there's actually another interesting consequence of the proof of the blow-up lemma. So if you go back through, you know, the way I said it, we have these targets and we're embedding, but the more you think about it, the target sizes are large. You know, in the end we want at least one, but really they're kind of large in respect to the number of parts. So generally that means there's not just one copy of H and G, it would mean there's actually many copies. So on the order of V of G to V of H copies of H and G. So that's kind of a consequence of the proof, right? So we could have stated that a bit more formally, but really, you know, the number of targets at each stage is something more like linear at n. So actually, you know, if you say how many of those end up successfully working, if you count the number of possible copies from the targets, you'll see that this was what would work out. And a different way to kind of say that more formally is what's called the removal lemma. So it says that for every epsilon greater than 0, there exists a delta of epsilon h greater than 0, such that if a graph G has at most delta V of G, V of H copies of H, then G can be made H-free by removing at most epsilon V of G squared edges. So this is really nice. It's also a consequence of kind of the blow-up lemma and thus the regularity lemma, and doesn't have really anything to do with Turan's specifically, but it kind of does, right? Because this is in essence a generalization of Erdos-Stone, right? So here instead of doing blow-ups, though, we're having many copies. That's the difference. But again, it will follow in the same way. So maybe just appreciate what this says, right? So we knew Turan's gave us a bound on the number of edges. And so if you're not close to being that, not only can you find a la Erdos-Stone a blow-up of, say, a triangle or a KR, you actually get kind of not linearly many, but you know, V to the right number many copies of H is the contrapositive of this. So, you know, so if there's few copies, the reason there are few copies is because you're really close to being H-free. So how do you prove this? I'll just give you a quick sketch. So again, regularity graphs. We may assume the regularity graph is H-free by the proof of the blow-up lemma, right? So if you weren't H-free, if you found an H, if you understood the blow-up lemma and you choose the parameters in the right way, you'll actually be able to get kind of linearly many for each target in some number that only depends kind of on H and epsilon, and then we'll get kind of, you know, that with a delta. So that, we won't go through those details, but that's the idea at a high level. And then the claim is you can make G H-free once you realize the regularity graph is H-free by removing the silly edges. So those are the ones from the trash. Let's remove all of the trash. We'll remove the irregular pairs, and we'll kind of remove the low density pairs. And then the claim is that you'd actually kind of have to be H free then. So, we won't go through that, but that's on a rough level is saying we could kind of clean it up, right? And then if we could find an H, we'd like to say we would have found it in a blow up somewhere, right? We would have found it across the parts, so we would find it in some blow up, and that would contradict what we have here. So again, thinking of H as a fixed graph, which I didn't say. So, okay, that's the removal lemma. So today we learned lots of good stuff. We learned what is the Turan number, at least kind of non-bipartite graphs, but even learned something about them. It's related to the chromatic number. That follows from the Erdos-Stone Theorem, where we're looking at blow-ups of cliques. That follows from the blow-up lemma, a consequence of the regularity lemma, which says if we can find kind of a subgraph of the regularity graph, we can find it in the graph. We can actually find blow-ups of it. So if you find a clique, you can find blow-ups. And even talked about the removal lemma, which instead of talking about blow-ups, talks about having kind of many copies. If you don't have many copies, then you can be made H-free by removing not too many edges. So that's what we'll do. Next class we'll turn into talking more about Ramsey numbers and applying the regularity lemma and blow-up lemma there. And again, regularity graphs as well. So until next time, see you then.